In Chapter 9, Part 3, Covalent Bonding and Hybrid Orbitals, we're going to continue to think about how do molecules form. So we know that two elements come together, they have orbital overlap, but what does that actually mean in a covalent bond? So covalent bonds arise from positive orbital overlap. When we think about this, we can have ionic bonds where the electrons are not shared, and in a covalent bond, the electrons are shared. So we have shared electrons. And these shared electrons are in an orbital, and these two orbitals overlap. So let's think about hydrogen. We know that hydrogen, we have two H atoms, we have a nucleus, we have a single electron in the 1s. And so these two have to come together, and they have to overlap. And when they overlap, we're going to get our two s orbitals. So the s orbitals overlap. And this positive, or this situation in the center, this is where the bond is formed. This is our bond formed by positive orbital overlap. So there are other types of orbital overlap, which is a negative interaction where you do not get a bond. In this case, the two orbitals overlap, and this bond is formed by the positive orbital overlap. So we would draw this as hydrogen connected to hydrogen, but we have these two orbitals that came together. So let's look or think about HCl. So we know that the the hydrogen is an S, the chlorine has p orbitals, which we know look like this. And so we can have the same type of orbital overlap. We have a hydrogen, we have a chlorine, and we still have our bond created. And so I haven't drawn the other chlorine orbitals that are in other orientations. So we see this creation of bonds, and we can see this by positive orbital overlap. And so one of the things that's worth thinking about is how close do these have to be? So the optimum distance between these, if we have our radius down here on the bottom and we have an energy scale, there is an optimum distance. And so this distance right here, where we see this energy well, which is where things are favorable, this is where we get bond formation. If our radius for these two elements is over here, we're going to see repulsion. If you think about two magnets that you shove together, at some point they will start to repel each other. Or you will basically try to put them on top of each other, and that doesn't work either. So you can get some bond, or a slight bond here. But if the radius is too far, we will get them too far apart to interact. So this ideal distance is really where the bond radius or the bond comes from. So as the two elements are further and farther apart, they don't interact. If you have two magnets and they are too far apart, they don't interact with one another. But you also can't shove them all the way over here to where they are so close together, they're on top of each other. There's a happy medium where they interact with one another. So we see this for any bond that is formed, whether it's HCl, ClCl, carbon, hydrogen, any of these. But when these orbitals overlap, so let's think about CH4. So we have carbon with 4 hydrogens, and it looks like this. And we know based on the structure that we have a steric number of 4, which is tetrahedral, and so we end up with this structure. So, but if we think about the orbitals, we know that hydrogen is a circle, and carbon is a 1s2, 2s2, 2p2. So we know that we created 4 bonds here in our structure, but realistically, did all of the electrons interact with the p orbitals? So if they did, we would have expected something that was in 3D space. So this structure does not match the known orbitals, aka the p orbitals. So what am I saying? P orbitals, we know, are on the x, y, and the z axis. So if this is x, y, and z axis, they're all 90 degrees apart. So if you were to, and I will use a different color, draw all of my p orbitals, and we will make this one kind of look like this. So what you cannot see in this absolutely hard drawing is that those orbitals are all at 90 degrees to one another. If we look at our tetrahedral molecule, we really know that they are 109 degrees apart. So these are 109. And these orbitals here are all just 90 degrees. And so the question really becomes, how is this possible? And so we're going to start to create hybrid orbitals that are going to give us the ability to say and think about how the molecules that we know exist form. So there are a couple of key facts. There's a fixed number of orbitals, so the number that mixes together equals the number of hybrid orbitals. So let's think about how this molecule is created. We know that we are going to have 4 equivalent orbitals. So let's look at this was the 1s. For carbon, we have the 1s, the 2s, and the 2p orbitals. So we have a structure that looks like this. We know in order for this to work that 2 electrons have to come together. So even if we were to have said it was p orbitals, we could have really only created a bond here and a bond here. So if 2 electrons have to come together, one from the hydrogen and one from the carbon, in order to make this doesn't really work. So what we're going to see instead is a hybridization. So to create a hybrid orbital, I'm going to mix together known orbitals. So we need to make 4 equivalent orbitals. And so we're going to take our carbon, and then we're going to mix together these. So you can ignore these red orbitals, or the red electrons. In this case, we're going to mix 1 s orbital plus 3 p orbitals is going to equal 4, what we're going to call an sp3 orbital. So now our carbon electron diagram would be 1s, and all 4 of these are going to be the 2 sp3 orbitals. So when we put the 6 electrons that carbon has, what we see is 1, 2, 3, 4, 5, 6. So now there are 4 equivalent orbitals that could be created. So it's important to note that the number of orbitals that go in, so we added 1 plus 3, that gives us 4. So we're going to look in the next section, or in the next second, at the different types of orbitals that we can make. In this course, there's a limited number of types of types of orbitals that we can create. So the types of hybrid orbitals we can create in this course: the sp hybrid, the sp2, and the sp3. So we really only have 3 different types of hybrid orbitals. You may have heard in other courses of sp3d and sp3d2. While some textbooks talk about this hybridization, one of the things that we believe is that the sp3d and sp3d2 are not observed in this manner. So while we know that these structures exist because we have steric numbers 5 and 6, one of the things we also know is that this is not exactly true. And so we are not going to hybridize in this way. We are only going to focus on sp, sp2, and sp3 hybridization. So these are a big resounding no. So let's go and talk about the sp, sp2, and sp3. So if we were to think about for sp, we are going to combine a single s orbital and a p orbital. So let's look at BeF2. So beryllium has 1s, 2s, and the 2p orbitals. It has 2s electrons in Be. We know that fluorine has the 1s, 2s, 2p. And so fluorine has a single electron in a p orbital, so we can create a bond using this orbital here. This is going to be used in bond formation. Structurally, we know that BeF2, so BeF2 has 2 valence electrons plus 2 times 7. So when we draw a structure, we put Be in the middle. And this is our structure. So Be can violate octet by not having enough. And so when we look at this, we need the ability to mix orbitals in order to create a linear orbital. So for beryllium, we're going to take our 1s, and then we have the 2s and these 2p orbitals. And we need to mix together some of these orbitals. We're going to mix together the number of orbitals that we need. So we're not going to mix everything together, just what we need. So we have the 1s, then we have a 2sp, and then we have left 2 pure p's. So these here are pure p orbitals. This is a hybrid of an s orbital plus a p orbital. So when we put in our 4 electrons, we have 1, 2, 3, 4. So these are going to continue to follow all of the filling rules that we've already learned. So now we can see that there are 2 equivalent orbitals that are mathematically 180 degrees apart. So this allows us to see this. So let's think about a different one. So let's look at how we might arrive at an sp2 hybridization, or what does that mean? So if we look at BF3, we know that the number of valence electrons is 3 plus 3 times 7, which is going to give us a structure that's going to look like this. So now we know that the bond angle here is 120 degrees. None of the p orbitals exist that way. So if we start to look at the electron configuration of boron, we have the 1s, the 2s, and 2p's. So we're going to put in our electrons. So we have a single electron in a p orbital and 2 empty p orbitals. We again know that fluorine is the 1s, the 2s, the 2p, and its electron configuration looks like this. So we can use the p orbital to interact, but we need 3 equivalent orbitals. So for boron, we're going to mix together 3 orbitals. We're going to mix the s, the single s orbital, let's just write an s, plus 2 p's. Or you could think about this as s plus p plus p. Because since these are in the n equals 2 shell, the 2 is a little murky in this case. So now we're going to mix these together. And for boron, we're going to end up with the 1s the sp2 and the 2p. So we'll put in our electrons. And when you mix 1s and 2p orbitals together mathematically, you get 3 equivalent orbitals that are 120 degrees apart. So when we look at the types of hybrid orbitals, we have the sp. This is 1s plus 1p, and that equals 2 sp orbitals. So there are now 2 equivalent ones, and they are 180 degrees apart. For an sp2 hybridization, it's s plus p, and that gives us a total of 3 sp2 orbitals that are 120 degrees apart. For the sp3 hybridization that we saw in methane, we have an s orbital plus a p orbital plus a p orbital plus a p orbital, which gives you 4 sp3, and these are 109 degrees apart. So the way that we identify the hybrid orbitals, so when we look at the names, this tells us which orbitals are mixed together. So the superscript tells you the number of orbitals that are mixed together in this case. So to determine the hybridization, it's relatively simple. Draw the Lewis dot structure, determine the VSEPR electron geometry. So this means the steric number. And specify the hybrid orbitals that create this geometry. So what we learned in the previous slide, or just a second ago, was that the orbital orientation tells us different structures. So in this case, what we're going to notice is that certain steric numbers correspond to specific hybridizations. So for a steric number of 2, we know that the bond angle is 180 degrees. We know that a hybrid orbital, sp, is also 180 degrees. So for a steric number of 2, this is always an sp hybrid. For a steric number of 3, with 120 degrees apart, it's going to be an sp2 hybrid. For a steric number of 4, we have 109.5 degrees, or 109 degrees, and that is always going to be an sp3 hybrid. And so in the examples we're going to start looking at, what we'll also notice is that sometimes there are leftover p orbitals, and those are going to be really important. So in the next video, 9.4, we're going to look at multiple bonds and where double bonds really come from. Those come from the leftover p orbitals. So in order to have a double bond, you have to have pure p orbitals. So let's look at a couple of examples. So let's look at CO2. So for CO2, our valence electrons will be 4 plus 2 times 6. And so we know that carbon will be in the middle, connected to oxygen. And so we see this structure. So the steric number here is 2, so we know that this is linear and an SN of 2. Now there are just 2 things connected, but they have double bonds. So in this case, for carbon, we have 1s, 2s, 2p, with our orbitals in this way. So now we're going to need to make a linear arrangement. We're going to mix together the 2s, an s orbital and a p orbital, to where we have the 1s, the 2 sp orbitals, and then the 2p pure p orbitals. So in this case, we're going to fill our electrons. We have 1, 2, 3, 4, 5, 6. So this gives us the linear geometry. These leftover bonds, or the leftover orbitals, are going to be used to make double bonds. And so in the next video, we'll learn more about why we have leftover p orbitals that are used in this case. So the hybridization here is sp. So can we also determine the hybridization of the oxygen in this case? So oxygen, if we were to look at this, has a steric number of 3. We have one lone pair at the top and another lone pair at the bottom and a single bond. So we have a steric number of 3 here, which we're going to come to learn means that it's sp2 hybridized in order to give us the 120 degree orientation that that element contains. So what about for H2S? So we'll move this down here. We have H2S. So in this case, our valence electrons is 6 plus 2 times 1. So our Lewis dot structure, we have 2 hydrogens, which use 2, 4, 6, 8 valence electrons. So we know that this is a steric number of 4. And so we're going to put our 2 electrons here, or our 2 hydrogens. We have 2 electrons over here. And you could have put these in any orientation around this sulfur molecule. So we know that this is the tetrahedral bent is the molecular geometry. So we have a steric number of 4. But let's look at the electron configuration for how we can do this. So if we have sulfur, which is, we will just use the noble gas configuration of neon, 3s, 3p. And so it has 6 valence electrons, 1, 2, 3, 4, 5, 6. So in this case, we can see that these are, we need to mix these together. So we're going to mix all of these together. And the reason we can't just use these 2 p orbitals is because they would be 90 degrees apart. And we know that this is just much, much less than 109, on the order of 105. Which is not 90 degrees, even though 90 degrees is much, much less than this. So we're going to mix these together to where we have neon and the sp3 hybrid orbitals. So we're going to put in our 6 valence electrons, 1, 2, 3, 4, 5, 6. So now we have 2 pairs or 2 orbitals that are ready for bonding. These are bonding. Now these 2 filled orbitals, these are our lone pairs. And so the lone pairs we know are in the same orientation as these 2 bonds that we're making. So we can see that all of these mix together to create our sp3 hybrid center on this sulfur. So the hybridization of this is the number of orbitals that we mix together. It's super important to realize that the number of orbitals that goes in is the number of orbitals that we got out. So the other example, BF3, we did a little bit earlier, so I won't do it again. But let's ask ourselves, can we predict the hybridization of any atom in a large molecule? So I'm going to draw a molecule and then we'll look at it. So we have this molecule, and at the top you can see we have a Lewis dot structure where we see a string of hydrogen, oxygen, carbon, carbon, and then some hydrogens passed around. So in this case, this is a much larger molecule than we've ever looked at in this video, but you were provided a Lewis dot structure. In chapter 9, part 5, we'll look at drawing bigger molecules, but we can look at a Vesper structure and determine the hybridization of any element based on the steric number. So let's look at this carbon over here first. So it has 1, 2, 3 things connected to it. So we have a steric number of 3. That means it's trigonal planar. And so we know that that has to be an sp2 hybrid. And when it is an sp2 hybrid, it also has 1 pure p left. So we have a steric number of 3. So let's look at this other carbon that I'm now going to color in green. So what we can see here is that it's connected to 1, 2, 3 things. So we have a steric number of 3. It's still trigonal planar, or also. And that's going to be an sp2 hybrid plus 1 p orbital. So what about the oxygen that's left? So we can look at this and we can see that it's connected to 1, 2, 3, 4 things. So we have a steric number of 4, which makes it tetrahedral as the base. And when we go back, it is going to be bent. And so we know that it's much, much less than 109 or about 105. In this case, we know that it's going to be an sp3 hybrid. And all of them are going to have been mixed together. So if we look at oxygen, we have 1s, 2s, 2p, and we've mixed together our 6 valence electrons. So we're now going to mix all these together to create the 1s. And then our sp3 hybrids, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons, to where these 2 are for the bond, and these 2 are our lone pairs. So it's important to note that for any molecule we see, we can actually determine the hybridization. Now, hybridization in this course only happens for steric numbers 1 through 4. And steric numbers of 1 don't exist. So we only see that in these lower things. If it is a hypervalent molecule, the mixing of those orbitals is inconsistent with mixing to hybridization of d orbitals and s and p orbitals. So we are not going to see hybridization in that case.